So first thing we're talking about here are our parent functions. We have talked about parent functions before. We talked about them back in Algebra 1. Does anybody remember what a parent function is? No? Nobody. Your parent function is the most basic form of a function. So every kind of function that we have has a parent function, our most basic form of it. And then all of the other functions in that family are just that parent function moved around your graph. Moved up, down, left, right. They made it wider. They made it more narrow. They shrank it. All that good stuff. But it all goes off of our basic parent function. So our first one, this one here, you guys have been learning since about middle school. What kind of a function is this? Linear. You need to be able to recognize your linear function by the graph, which would just be a straight line, or by the equation of it. So if we look up over here, your linear function just has an x to the first power, or whatever letter they've decided to use. It could be a to the first power, b to the first power, all that good stuff. There's only one kind of line that is not a function. Does anybody remember it? One line. Jamila? Vertical line. No vertical lines, because then they fail the vertical line test. They're not even a function. So when we talk about our linear functions, we're talking about every other kind of line except for your vertical line. So let's go through and talk about some key features we have here. With our linear functions, we have a slope to them. What would be the slope of this one? Remember, pick 2 points. I go up 1 over 1. So our slope is a 1. The main thing here with your linear function is that your slope is constant. It's always a 1. The entire graph is always going up 1 over 1, up 1 over 1, no matter what section of it you're looking at. What would be our y-intercept? 0. How about our x-intercept? That would also be 0. Our x and y-intercept are both at the origin. Again, because it's our parent function, that's where it is. We take our graph, we move it, it's not always going to be there. What would be our domain of our linear function here? Again, with domain, you want to ask yourself, can it be every single x value possible? Yes. So we write x as an element of the reals. How about for our range? Can it be every single y value possible? Yes. So how do we write that one? Good. Y is an element of the reals. So for your day 5 that you were supposed to go through, we're going to talk about even, odd, and neither functions. Even function means that it's symmetric over your y-axis. So is this linear function symmetric over my y-axis? If I take my paper on my y-axis and I fold it in half, is it going to line up? No. So this one is not an even function. Your odd function, it can be reflected through the origin. So you got to think back to geometry a little bit. Is this line reflected through the origin? If I were to reflect it through the origin, would I get the same line again? Yes. So this is an odd function. Would this graph be increasing or decreasing or both? Not both. Start at the leftmost point of the graph. If I follow my line, am I increasing or decreasing? Increasing. It's increasing the entire time. So the notation we would use for that, if they asked you to state the interval over which it's increasing, you would write x as an element of the reals because it's always increasing. That's never going to change with our linear functions. They're always increasing or they're always decreasing. Okay. Couple other things. Would this be a 1-to-1 function? Remember, 1 to 1 passes both your vertical line test, which we already know this one does, and it passes your horizontal line test. Yes, so this would be a 1 to 1 function. Is this an onto function? Remember, onto means it uses every single range value possible. Will it? Yes. So this is onto. And then the other word we learned, or we should have learned, is this is a continuous graph. You can draw this line without picking your pencil up off the paper. It continues throughout the entire graph. There's no breaks in it. All right. Let's take a look at our next one. What kind of graph, or what kind of function is that? Begins with a Q. Quadratic. This is a quadratic function. So again, you have to be able to recognize that U shape to it. That's what tells us it's a quadratic function. If you look at the equation, it's got an x squared term in there. That makes it your quadratic function. Do you remember what we call the shape of that graph? That one had a special name. Parabola. But again, parabola only describes the shape. It is not the kind of function, so be careful with that. It's a quadratic function. So with our quadratic functions, we don't talk about a slope like we do with our lines, because our rate of change is always changing in this one. Do we have an x and a y intercept here? We sure do. What is it? 0, right here. Hit your x-axis at 0, hit your y-axis at 0. So we have an x and a y intercept of 0. What do we actually call that point in the parabola? Does anybody remember? Vertex. There's another word for it too. Vertex or turning point. They like to use those two words interchangeably. For this one, it would be at the point 0, 0. Whenever you write it, it's a coordinate point. So you got to have parentheses around it, x value, y value. Okay, let's do our domain and range. What would be our domain here? Can we use every x value? Yeah, we can. That graph's going to keep on going. It's going to keep on moving out sideways slowly, but it will keep going there, so it can use every single x value. Will it use every y value, though? No, it's never going to be down here in the negative. So what would our range be? Y is greater than or equal to 0. Okay, so let's figure out what kind of function. Is this an even function? Is it reflection over the y-axis? Yes, this one's an even function. Could it ever be even and odd at the same time? No, that's just silly. It would never be even and odd at the same time. It's either even, or it's odd, or it's neither. All right, next one. Increasing, decreasing. I'm going to put that over here. Is this one increasing, decreasing, or both? Both. If I start on the left part of my graph and I follow my graph, we start off doing what? Decreasing. So this side of it's decreasing. After our vertex, we start going back up. The graph is now increasing. So this one has both decreasing and increasing values. It is decreasing to the left of 0. These values to the left of 0 would be less than. When x is less than 0, it's decreasing. When x is -1, -2, -3, -4, at those points in time, it's all decreasing. So how would we write our increasing? When x is what than 0? Greater than 0. So when your x is +1, +2, +3, all those values greater than 0 is when it's going to be increasing. Range, decreasing. Is this graph continuous? Could I draw my whole shape without picking up my pencil? Yes, so this graph is continuous. Would this graph be 1 to 1? No, it does not pass your horizontal line test. It's not 1 to 1. Would this graph be onto? No, because it's got all these negative values down here that it's never ever going to use, so it's not onto. It would just be a continuous, and it's an even function. All right, how about our third one down here? What kind of function do we have there? Not exponential. Use the formula as your hints. That's x what? To the third, which we refer to as cubed. So this is our cubic function. I'll never forget my teacher when she taught me this. You guys know Saturday Night Live with John Travolta, the movie? And he always strikes his little disco pose like this. She called it the John Travolta curve. Never could get that out of my head ever. Kind of looks like his little curve. His arm over here is going up, the other arm's going down. This is John Travolta curve. So this is our cubic function. Not as well known. You guys haven't seen this one as much. So let's start with our intercepts. X-intercept, Y-intercept. What are they? Both would be 0. Again, it crosses at the origin. Those are your x and your y-intercepts. Pretty much most of your parent functions, your x and y-intercepts are going to be zeros for your parents. Okay, let's take a look at the next part. We don't have a vertex or a turning point for this one like we did in our quadratic because it doesn't turn and go back up. Let's do our domain and our range. What would our domain be for this graph? Element of the real. This is going to keep on going. So this one will use every single x value it possibly can. How about for our range? Y is an element of the reals. Very good. It's going to use every single y value that it possibly can. Is this graph increasing, decreasing, or both? Increasing. Again, if you follow it starting from the left, your pen is always going up. It slows down in the middle, but it's still increasing ever so slightly, and then it picks up again. So this one is increasing the whole time. Again, when we say it's increasing the whole time, if they asked you what the interval was over which it's increasing, that would be x as an element of the reals. Okay, is this function an even function? Nope, it's not symmetric over my y-axis. Would it be an odd function? Yes, this is reflected through the origin. If I kind of took this and I flipped it, it would be the exact same curve, so this is an odd function. Is it a one-to-one function? Would it pass both vertical and horizontal line tests? Yes, it would. So it's 1-to-1. Is it onto? Does it use every single range value possible? Yep, so this one's onto. Is it continuous? Yes. 1-to-1, onto, and continuous. There we go. A few more. All right, number 4, what kind of function is that? Absolute value function. It does have a vertex. So let's start with our x and y intercepts. What are they? Both 0. What also happens at 0, 0? Yeah, our vertex. Also known as our turning point right there at 0, 0. Now let's do domain and range. What would be our domain? X is an element of the reals. It's going to be every single x value. What would our range be? Y is greater than or equal to 0. Is this an even function? Is it symmetric over the y-axis? Yeah. Would this be a one-to-one function? No. Totally would fail your vertical line test or your horizontal line test. Is it onto? Nope. Is it continuous? Yep. This one has both increasing and decreasing parts to it. It changes at your turning point, which is why we call it a turning point. So first we're doing what? Decreasing. And then the second half of it is when we start increasing. Again, it changes from increasing to decreasing when x is 0. So our decreasing part is for what values of 0? Greater than or less than? Less than. So when x is less than 0, we're decreasing. So therefore, increasing is when x is what? Greater than 0. All right, let's move on to the next one. What kind of a function is our next one? Square root function. So we'll start going through our little list. X-intercept, y-intercept, what are they? 0. Doesn't really look like it, but it does go down and it touches the origin at 0, 0. So those are our x and our y-intercepts. What would be our domain? Remember, this is one of our problem children. Our domain is not x as an element of the reals this time. It's not using every single x value. Greater than or equal to 0. If you remember, when I taught you this, to find it algebraically, you had to take everything under the radical and set it to be greater than or equal to 0. That's how I knew that's what my domain was going to be. So what would our range be? Y is greater than or equal to 0. That one won't go negatives also. Is this graph continuous? Yes. Is it one-to-one? Yeah, passes both vertical and horizontal line tests. It's one-to-one. Is it onto? No, because it didn't use any of these negative range values. Not onto. Okay, x. Oh, is this graph increasing, decreasing, or both? Increasing. Now with this one, yes, it's increasing for the entire part of the graph, but we have no x values over here in the negatives. So you're increasing, since it's everything would look a lot like your domain, it would just be it's increasing when x is greater than or equal to 0. All right, last one, last parent function. Does anybody know what kind of function that is? We don't use this one's name all that often, really. This is a rational function. Rational functions are your fractions, which if you remember, those were special cases. Do we have an x or y-intercept here? No. No x-intercept or y-intercept. Now again, that's not always true. If I take my graph and I shift it down or up, I would then have one, but for right now we don't in our parent function. What would be our domain here? Again, this is one where I taught you. If it's a fraction, you take your denominator, set it equal to 0. You would solve for x, but in this case, there's nothing I really need to solve. I get x equals 0. So our domain is everything except x can't be 0. Because when x is 0, that gives us a vertical asymptote, remember. So that means the graph gets closer and closer and closer to it, but it will never actually be 0. What would our range be? Remember, our range always looks very, very similar to our domain in these ones. Y is an element of the reals, except it cannot be what? 0. Because again, we would have a horizontal asymptote at 0. That graph's going to get closer and closer and closer to a y value of 0, but it will never actually be 0. So this graph has asymptotes. It's got two of them, a vertical and a horizontal. So it's got a horizontal asymptote. That's what my HA is at y equals 0. Vertical one at x equals 0. You've only learned how to calculate the vertical algebraically. You'll learn how to calculate the horizontal in pre-calculus algebraically, not here. Colon. Okay, is this an even function? Are we symmetric over the y-axis? Nope. Is this an odd function? Yes. Is it 1-to-1? Yes. Is it onto? No, because it can't equal 0. So it's not using every single range value possible, so it's not onto. Is this a continuous graph? No, this one is a discontinuous. Again, I can't draw this part of the graph and then somehow magically get up here without picking up my pencil. So it's discontinuous. So hopefully that was a good little review for you guys. So let's take a look at our next page. We are doing transformations. We've done transformations before. We did them back in Algebra 1, but we're going to go over them again. So every parent function can be moved around the graph. You can reflect it, you can translate it, you can dilate it, you can do everything with it. So there is a specific order to which you do your transformations, though. Starts off with any horizontal shift. So, moving left or right is the one that always happens first. In your equation, that would be your b value. So if we take a look at my examples up here, you'll notice your b value is always directly next to x. So that's why we take care of that one first. We always start with what's closest to x, and you kind of work your way out with your transformations. Horizontal shift, you can't get any closer. It's right next to x. So that's the one we do first. Next, we do our reflections. And we actually have two types of reflections. We'll get to that in next page. After that, you do any stretches or shrinks. Those involve your a value of your equation. So if you look up above, your a value is always the one that's out in front. And then our last one would be any vertical shift. And that's the c value in the equation. That's always at the end. It's the furthest thing away from your x value. That's why it happens last, moving up and down. So what we're going to do is we're going to go through, practice some graphs, and we're going to go through each of the rules just to refresh your memory about your horizontal shifts, your reflections, your stretches, your vertical shifts. And all of these can be done in the calculator. Like if we look down here at this example, you could type in x squared minus 5, get yourself a table of values and graph it that way. That is always an option. What I'm going to be showing you today in class is how to do it based off of the transformations. So you don't always have to get a table of values. Sometimes going off the transformation can be a little bit faster. So what we have done already over here is I have already graphed our parent function for us, f of x equals x squared. We're going to start with h of x, which is going to be x squared, which if you notice is the same thing as I have up there, minus 5. So since the minus 5 comes at the end, this means we're going to shift it down 5 units. Now, if you're going to graph using the transformation rules, you just have to write what are the transformations. This time it's moving it down 5. So what you want to do is you want to pick the points on the graph that actually hit the box as well. You don't want to go with any of the decimal ones. So I'm going to start with my vertex, and I'm just going to move it down 5. 1, 2, 3, 4, 5. So there's my new vertex. So if I look to the right of my vertex, I've got a point there at 1, 1, so I'm going to move that down 5. 1, 2, 3, 4, 5. And then that same point is over to the left of the vertex, so I move that one down also. So then if I follow my graph, I see another point at 2, 4, so I'm going to move that down 5. And the same thing happens at negative 2, 4. So I move that one down 5. And then at 3, 9, move that one down 5. So once you have your points, you connect them. And I'm going to label that as h of x. You always need to at least label it with which function is it. The f function, the h function, g function, whatever letter they're using. So for our next one, j of x, I'm just going to rewrite this and put it in standard form. So I'm going to put my x squared first, so that's really x squared plus 3. So which way do you think this one's going to move? Up, how many? All right, so I'm just going to write up 3. So I'm going to go back again. You got to start with your parent function. And you're going to take each point this time and move them up 3. You're not going to be able to get as many points because then it starts going off the graph. Then you label that one as j of x. And I think once you can remember what each transformation is, this actually makes it a little faster than typing it in the calculator. So then our little rule to fill in down here. If we add a number at the end, you move up that many units. So they're using the letter C, so you move up C units. If you subtract it, that means you're moving down that many units. Now I show you this too because they love to use this notation. They'll talk about two functions and they'll say the second one is the first function plus a number. So you got to remember that means you're moving it up. All right, so let's take a look at the next one. Next one are horizontal shifts. So we're moving left, right. Now when you're moving left, right, again, you are going to have a number right there with the x. So as you can see here, they extended out the parentheses to make sure that that number is included. That's showing you that it's with the x. If those parentheses weren't there, then these would be an up-down shifts, not a left-right shift. So these are going to be actually opposite of what you think. If you're adding a number directly to C, you're actually going to move left that many units. And if we're subtracting a number, that means you're going to move to the right that many units. So if we take a look at our example up here, if I have x minus 2, that means I'm moving which way? Right. How many units? So I'm going to write right 2. So I'm going to take each point. I'll start right here with my x and y intercepts. I'm going to move that to the right 2 and put my new point. -1, -1, I have another point, so I'm going to move that to the right 2. 1, 1. I'm going to move that to the right 2. And then the very tips. So that gives me my h of x function. So how about our next one on there? Yep, adding means I'm going to move left 4. So I'm going to use those same points that I found to move it to the right, and I'm just going to move each one to the left 4. 1, 2, 3, 4. 4. And that's going to be our new function j of x. So going on to our dilations. If you multiply your function times a number greater than 1, so if you multiply it times like 2, 4, 5, any number, that stretches your graph by a factor of a. So this time we're using the letter a. So whatever number a is, you're multiplying. If it's between 0 and 1, that means it's a fraction, like 1/4, 1/3, 1/2. This shrinks the graph by a factor, again, of a, whatever that number is. These ones are a little bit trickier, but when you're doing your dilations and you have your graph over there, one thing to keep in mind is you're only going to multiply your range. Your x value does not change when you're doing your dilations, only your range value changes. So if I am multiplying times a 2, we would write that as a stretch by a factor of 2. That's how we would describe it. And I'd go to each point. Well, 0, 0 is not going to change. But I would go to each point and I would multiply my range value times 2. So like I'd go to the point 2, 1. My range value is a 1. 1 times 2. I said that wrong. Moves it up to 1, 2. Actually, I said 2, 1. Again, you only multiply your range value. So I go to the point 2, 2. My range is a 2. Multiply it times 2. That makes it move up to a 4. So 3, 3 would change to what? 3, 6. 4, 4 would change to 4, 8. And then since it's an even function, it repeats that over on the other side. So negative 1, 1 would become negative 1, 2. And then negative 2, 4. Negative 3, 6. And negative 4, 8. So if we have a 1/4, this is going to be a shrink by a factor of 1/4. So again, we're only multiplying the range times 1/4. So again, 0, 0 is not going to change. That's going to say 0, 0. If I'm at 1, 1 originally, that means it's going to become 1, 1/4 when I multiply, because I do 1 times 1/4, I get 1/4. 2, 2 becomes 2, 1/2, because again, if I multiply my range, which was a 2 times 1/4, I get 1/2. 3, 3 would become 1. Does anybody know? Yep, 3, 3/4. And then 4 is a nice even one. That would be 4, 1. So sometimes what you can do is you can kind of skip over these ones that are fractions and just make sure you plot 4, 1, since that's a nice even whole number. You know that number. Another one that works out would be 8, 2. It was 8, 8. But 8 times 1/4 would give me a 2. And then again, it repeats it over on the other side. So I have negative 4, 1, negative 8, 2. You can skip around to just the whole numbers. If that's difficult for you, use your calculator. Don't hesitate to use your calculator. I want to make sure you guys get it right. So now some people in my other class didn't understand why the stretch makes it more narrow and the shrink makes it wider. Because what you have to think about is the stretch is taking these points and it's stretching it up and it's moving those points up, which makes the graph become more narrow. Your shrink is taking these points and they're shrinking them down, which ends up making your graph become wider. Okay? Our last one are reflections. And then we're going to do some practice examples. If your negative sign is right in there with the x, you're going to reflect over the y-axis. If your negative sign is out in front, you reflect over the x-axis. So let's take a look at our example. So first one we have, the negative is with the x, so this is going to be a reflect over the y-axis. We did a whole bunch of reflections last year in geometry. You guys should know this. Again, we're still going to have the point 0, 0. That's not going to change. But the point 1, 1 would become the point negative 1, 1. And then let's see here, another nice point. 4, 2 would become what? Negative 4, 2. 9, 3 would be negative 9, 3. So there would be our reflection over our y-axis. And all of your x values became negative. So when our negative is out in front, this one is a reflect over the x-axis. So again, when I go to graph that, I still have the point 0, 0. That doesn't change. But the point 1, 1 would become 1, negative 1. I've reflected over my x-axis, drop it down. 4, 2 would become what? Yep. And then 9, 3 would be 9, negative 3. So those are our reflections there. So now here are some examples of questions that they would ask involving our transformations. They can't make it nice and just give you one. They're always going to give you a whole bunch of them. So they're giving you the parent function, absolute value of x. They want to know how g of x is transformed from that one. They tell us to describe the transformations in order that occur from f of x to g of x. So whenever I do this, when you're doing your homework tonight, you want to write yourself a little list. Your horizontal shifts go first. So you always want to look, see if you have a horizontal shift first. Then it's your reflections. Then it's your stretches. Then it's your vertical. Be nice if I could spell that right. That's always our order that we go in. So our first transformation here. Is there a horizontal shift? Remember, that is in there with the x. Is there a number in there with my x? Yes. So I have a horizontal shift. If I'm adding 3, am I moving left or right? Yes. So it's first shifted left 3 units. 2 is our reflections. Do I have a negative sign in there? Yes, I have a negative all the way out in front. So that means it reflects over the x-axis. When the negative is all the way out in front, that's over the x-axis. Do I have a stretch or a shrink? Am I multiplying times something out in front? Yes, I'm multiplying times a 2. So this is a stretch by a factor of 2. Are we moving up or down? Down what? Down 4. There we go. Let's try another one. So again, we have our parent function, square root of x. They gave us a new function. They want us to describe the transformations in order that occur from f of x to g of x. Okay, so again, I'm going to go through my order. Do I have a horizontal shift? Do I have a number in there with my x? Yes. Now keep in mind, this is a positive 2. So which way does that move? Left. So we have a horizontal shift left 2 units. Do I have a reflection? Do I have any negatives? Yes. This one's a tricky one to see. This x is negative. It's minus x there. So what kind of reflection if the x is negative? Over the y-axis. So this reflects over your y-axis. Do I have a stretch or a shrink? No. There would be a number in front of your square root sign if it was. Like you'd have a 3 out there or a 1/4 or whatever. But that would be in front of the square root sign. We don't have that. Are we moving up or down? We're moving up 5 units because it's got that plus 5 at the end. Okay. A few more practice examples. This is going to kind of be like our classwork today. So we have 2 functions here. We have f of x, which is your x cubed. And then they tell us h of x is your f of x plus 3 and then plus a 1. They want us to find h of 1. So we kind of have to jump around a little bit here. We're finding h of 1. That means we're plugging in a 1 for every x that we see in our h function. So it becomes f of 1 plus 3 and then plus 1. I plugged in a 1 for all my x's. So if I clean this up, this becomes f of what? 4. And then plus 1. So what we do then is we kind of jump over here to this function and we plug in a 4 for x. Because that's what it tells us to do. It tells us to find f of 4. Which, what is 4 cubed? 64. So then I go back here and I plug in my 64 and I add 1 to it. So what's our final answer? 65. Number 4, we have a y-intercept of 12. They want to know what is the y-intercept after I multiply it times 3 and then subtract a 5. So if you keep in mind, think back to our notes when we were just doing the multiply. Did our vertex of our absolute value change at all when I multiplied? No. So the fact that we're doing this times 3, that's not going to change my y-intercept. Moving it down 5 will. So if my y-intercept is at 12 and I move it down 5, what would my y-intercept be? What's 12 minus 5? 7. So the y-intercept of our new function would be 7. Okay, number 5. Okay, so they've graphed f of x for us already over there. They now want us to add 3, subtract 1. So adding 3 to the x means we move which way? Left. How many? So we got to move left 3. And then this tells us to do down 1. So what you want to do is take each point, move it to the left 3, and then down 1. And I'm going to take this little minimum here, left 3, down 1. So I got my first little line there. Take my maximum, left 3, down 1. Then my last little part, 1, 2, 3, down 1. There's our new function, g of x. So we did part A, graph and label g on the axis. We did that. Part B, what is the smallest solutions to g of x equals f of x? So they are equal when the two graphs what? Cross. So which one of those is lower? Isn't this one here on the right a little bit lower? It's at like 1, 2, 2.8-ish. We got to estimate a little bit there. 2.7 would work also. So now they're telling us that a third function, h of x, is our g of x that we drew minus 3. So which way would it go if I do minus 3? Down 3. So I'm going to take each point, move them down 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. I'm going to label it h of x. So then they want to know, why does our new one, h of x, have no solutions with f of x, the original? Because they don't cross. Okay, so 6, if a parabola has the equation given, write an equation after a reflection in the x-axis and then a reflection in the y-axis. So if we reflect in the x-axis, was that negative sign out in front or with our x? Who remembers? Reflection in the x. Out in front. It was out in front like that. So what we have to do is take this, and you're basically just multiplying the whole thing times a negative 1. That's going to give you your reflection in your x-axis. You put the negative out in front. So if I multiply that through, we get negative 2x cubed plus 3x minus 8. Oh, that's not an equation. I got to put that back in there. Now it's an equation. Negative f of x equals that. So if we're reflecting over the y-axis, where does the negative go? It goes in for the x. So that means all of your x's in the equation you have to plug in a negative x for. So it's 2 times negative x cubed minus 3 times negative x plus 8. So then we just have to clean it up a little bit. If I take a negative x and I multiply it 3 times, is it still negative? Yes. So this would be negative 2x cubed. So then negative 3 times negative x would be a plus 3x, and then a plus 8. Is that exactly the same as our equation from part A? No, there's a little bit of difference. Minus 8 plus 8, so it does come out to be a little bit different. Now our last one, given the function g of x equals 1/2 x, what is the equation for the vertical asymptote after the transformation x minus 3 plus 2? To get our vertical asymptote, you take your denominator of your fraction and you set it equal to 0. This is what we were doing a couple days ago. So if I add my 3 over, there's our vertical asymptote at x equals 3. Same rules apply even though they did our little transformation to it.